Before going into the core of tractable approximate Gaussian inference for Bayesian neural network, I would like to acknowledge the contribution of my co-author, especially Nguyen and Nguyen, with whom I share equal contribution to the research work I'm going to present here. So the key finding we're going to cover together is that this method to perform the analytical inference in Bayesian network will allow us to make the initial inference for both the weight and bias parameter in feedforward neural network. It allows us in those neural networks to have end-to-end treatment of uncertainty from the input layer until the output layer. It allows doing online inference using one observation at a time, so batch size 1. And finally, and most importantly, it's efficient, meaning that it has a linear computational complexity with respect to n, the number of weight parameters in our neural network. And this linear complexity is the same as using backpropagation. And in terms of performance, it also matches the performance of standard neural network for a same architecture. So in order to go through these findings, what we're going to cover is first a review of the notion of Gaussian conditional, which is the backbone of what we're going to use in this TAGI method. Then we're going to look at the architecture for feedforward neural network that we're going to be studying here, and how can we approximate the distribution for our hidden units and activation units using GMA, what we're going to call Gaussian multiplicative approximation. Then we're going to see how can we build an AG-FNN approximate Gaussian feedforward neural network, and how can we do all the operation in that network building upon linear algebra. Finally, we're going to describe how can we perform inference for our weight and bias using what we name Tractable Approximate Gaussian Inference, TAGI. And finally, we're going to apply this methodology to several benchmark problems, either a 1D toy regression problem, several regression benchmark, and finally the MNIST classification dataset. So let's start with the background. What is that Gaussian conditional and why is it particularly useful? Okay, let's keep the context where we have a function like this, z equals WA plus B, where here A is a random variable. Let's assume it's a normal random variable with mean vector mu A covariance sigma A. B is also a random variable with mean vector mu B covariance sigma B. And W here is a matrix, n by n matrix containing deterministic constant. Okay, so A and B are random variable, which means that in turn, Z is going to be a random variable as well. So here, the nice thing we can do with the properties of Gaussian random variable is that we can express the joint PDF for, say, Z and A. Okay, how it's going to be? It's going to be also a multivariate Gaussian. And the mean vector for that joint PDF, we can obtain it by concatenating the mean vector from mu Z and mu A. And the covariance matrix we can obtain by concatenating again these covariance matrix, covariance for Z, covariance for A, and cross covariance between Z and A. And how do we obtain all these terms? We can obtain all of these using simple linear algebra. So the mean vector for Z is going to be W, my deterministic matrix, times mu A plus mu B, because B is a random variable as well. So sigma Z is going to be W times sigma A times W transpose plus sigma B, the covariance for my second random variable. And finally, the cross covariance between Z and A, it's simply the covariance for A times W transpose. Okay, then we can use this in a conditional context. So if we have observed, for instance, the output Z, and we want to know how much observing Z change our knowledge about A. So in that case, we can use the conditional context by saying this conditional PDF is going to be obtained by dividing my joint PDF that I have here for Z and A divided by F of Z. So in that context, it's still going to remain Gaussian, defined by the conditional mean vector and conditional covariance, which are all given by these equations here, where all the term we have in there we have already calculated, and where Z is my vector of observation here for my variable Z. So all of this, these Gaussian conditional concept, this is what's enabling both Gaussian process regression as well as state space model, also known as Kalman filter, okay, for time series analysis and many more applications. And here what we want to do is to leverage these computations, which are extremely powerful and extremely efficient, but this time into Bayesian neural networks. Okay, so before going forward, we have to see one more case. Before, only in our function, only A and B were random vector. But what if now W, A, and B are random vector? Okay, so A is a multivariate normal, W is also now a multivariate normal. So in that case, can I express my joint for both, or for the trio, Z, W, and A as a joint normal? Okay, in that case, I can do this. Okay, I know that the joint distribution for my tree variable is not going to be multivariate Gaussian, because here I have a product term between the random vector W and the random vector B. So in that case, because I cannot represent this as a jointly Gaussian random vector, the Gaussian conditional cannot be obtained here to update the information neither. And in neural network, our actual function really takes exactly this form, where again, that WA product is what's preventing us to already be using the Gaussian conditional to update the weight and bias in our network. So what we're going to see through this talk is how can we overcome this limitation and leverage the potential of Gaussian conditional into Bayesian neural networks. So let's look at the architecture to put everyone on the same starting blocks. So here I have a representation of a feedforward neural network. The leftmost layer is going to be my input layer. So the x's are going to be my covariates. So here you see the number of elements, the number of covariates is represented by this typeface x having the same letter as my variables. In blue, what you see here are my activation units. Okay, my activation units in a neural network is going to be the output of here my sigma function, which is going to be any generic nonlinear function that takes as input z, which are here hidden units. Okay, so activation units and hidden units are represented as superposed on top of each other. So z is simply a is simply a nonlinear transformation of Z, okay? So A, activation units, Z, hidden units. And the superscript I have here, L, represent the hidden layer in my network. So this is my input layer, my first hidden layer, second hidden layer, my Lth hidden layer, okay? Then I have my output layer, so the superscript with O is for my output layer. What differentiates the hidden layer and the output layer is simply that I typically don't have the same number of hidden units either on the output layer or the hidden layer, okay? I typically have more hidden units A here in my hidden layers than I have on my output layers. But this is not necessarily a requirement. This is just what's typically true. And finally, Y are my observed values, okay? And in that networks, I have several parameters. For instance, here, for going from one activation units on layer 1 to my hidden units on layer 2, I need to multiply my values here by some weights. Okay, so the weights here, it means I'm going to connect on the subsequent layer on the hidden units 1, and I'm going to multiply this weight by the 8th activation unit on the preceding layer. So the first index represents where does it connect to, and the second where it connects from. Okay, and I have also for each hidden unit a bias parameter. And all of this fully connected feedforward neural network, we're going to represent it in its compact form into what you see on the bottom here. Okay, the simplified notation, where here, instead of being all of these nodes separately, this is going to be a vector of nodes, same for the input up to my observation layer. And here I have a vector of parameter between each layer, which consists in both the weight and the bias parameter that allow to go from layers to layers. Okay, we're going to reuse that compact notation throughout the talk. So now let's look at what are the computational challenges associated with the feedforward neural network formulation. So if we want to go from a my activation units at layer J to my hidden unit at layer J plus 1, okay? I need to do the following calculation. So it's going to be A1 times W1 plus A2 times W2 plus etc. up to AA times WA plus at the end my bias parameter, okay? So this is the calculation I need to do to go from my activation unit at layer J to my hidden unit at layer J plus 1. But in our case here, this is not something deterministic. We want to treat it in a Bayesian way, in a probabilistic way. So now both W, A, Z, and B are all Gaussian random variable. Okay, so let's assume that W is a random variable with mean WA variance sigma W square. A is also a random variable, which is normal, mean mu A and variance sigma A square. So in that case, and this represents in a generic way, all the product terms we can see here, all the W times A, W times A. But what we saw previously is that in this case, the PDF for the product term W times A, it's not Gaussian, okay? It's not normal. However, what we're going to say, let's approximate this distribution for the product term WA by a normal distribution, where the mean vector and the covariance will have to compute, okay? So in that case, if we assume that this is normal, we can represent our joint knowledge for WA, W, and A, okay? And we can represent this by this mean vector and covariance matrix, where everything in black was already given from our prior knowledge. Everything in blue remains to be calculated, okay? And in this case, we can obtain an exact calculation for all the term in blue using moment generating function, okay? And this is what's behind what we call the Gaussian multiplicative approximation. So let's assume a generic vector. So here that X vector is not necessarily the input covariate in the neural net. We're trying to deal with this in a really generic way. So let's assume we have 4 random variables from X1 to X4, which are all multivariate Gaussian. So in that case, with our GMA, the Gaussian multiplicative approximation, what we're going to assume is that the PDF for the product of any pair of those variables is approximately normal, okay? So here in the stock, whether I use the label normal or Gaussian, means the same thing. They're both synonyms. So in that case, if I use the moment generating function, I can derive these equations. So the part that is in gray here doesn't really matter, okay? The only thing I want you to keep in mind is that these things have closed form simple solution. For calculating the expected value for a pair of Gaussian random variable, the variance for the product of that pair, the covariance between a product term and a single variable, or the covariance between 2 product terms. And using all this, we can completely fill our covariance matrix and build the distribution, which are going to be multivariate normal. Okay, but how good is that Gaussian multiplicative approximation? If we look at the product of a simple pair of 2 normal variables, we know this is far from Gaussian. Actually, we know it's chi-square, okay? The true distribution is the chi-square as represented in blue here, or Gaussian multiplicative approximation, which would add the same moment, so the same mean vector, the same variance, is represented in red here. So we can see it's a pretty crude approximation from the true PDF. Okay, but what we have to see is that when we use this in the context of the neural networks, so the product of A times W, A times W, A times W all lead to chi-square. However, to obtain my hidden units at layer J plus 1, I need to sum several of them. So if I have only 1 here, the approximation is pretty crude. If I sum 5, we see that the discrepancy between the true distribution and my GMA gets closer. What if I have 10? It gets even closer. And in practice, this is going to be the case. We're going to take the sum of several of those product terms. So our approximation, even if it remains an approximation, is not going to be such a bad representation of the real distribution. Okay, this is what we mean here by our Gaussian multiplicative approximation. One more step we need to see is that how do we transit from our hidden unit Z to our activation unit A, okay? To go from one to the other, we need to go through this transformation function, nonlinear transformation. And there are many choices. So it could be like in blue, that logistic sigmoid. It could be in red, that tan H. It could be in purple, that sharp ReLU, or it can be in yellow, that soft plus here transformation function. They're all admissible valid. But the issue here is that if Z is a random variable, we cannot propagate the uncertainty of that random variable through an arbitrary nonlinear function, okay? We can do it through the change of variable rule, but this is computationally really expensive, okay? So what we propose to do instead is to use the simplest possible approximation. So in that case, we're gonna locally linearize that nonlinear function at the expected value. For a specific expected value mu z, I'm gonna linearize that function by saying I'm gonna take the derivative of the function at the expected value times the value z minus the expected value plus the nonlinear function evaluated at the expected value. So if we look in practice, how does it look like? So imagine that I have a specific set of inputs and I obtain a given mu z. So for instance, here my mu z would be 0. This is my soft plus activation function. What I'm going to do, because what I'm looking for is what is going to be f of a, the output of that nonlinear transformation. So I'm going to linearize my nonlinear transformation at the expected value, and I'm going to be able to analytically calculate, because the input is normal, the output is going to be normal as well, for f of a. What if for another set of input covariates, I would have obtained another mu z, then I would linearize in another location, and I would have obtained another distribution for sigma a. The difference between the two, why it's not the same PDF, is because the slope is different depending on where I linearize, depending on what are my input covariates. Same for here. Here I'm in a part of the domain where the slope is going to be quasi-zero, which means that my PDF after transformation is going to almost collapse on itself because the slope is really, really small. Okay, so we know that this way of linearizing nonlinear function to propagate uncertainty through them is a crude approximation, because the right way to do it would be to use the change of variable rule, but this is expensive. There are more advanced methods such as using cubature computation, so like the cubature point estimation, in order to have more accurate estimation for the covariance, but this comes at a cost. So what we chose here is to use the simplest possible way to propagate our uncertainty by linearizing. And what we're going to see later on when we're going to look at the benchmark performance is that even that crude approximation allows us to reach the state-of-the-art performance of standard neural network. And this choice is really justified by its super low computational cost. Okay, so we've seen this is our structure for the approximate Gaussian feed-forward neural network. And going from the input layer to the first hidden layer is that structure W times X, where X can be a random variable. So we allow for uncertainty on our input layers. So we've seen how to handle this. It's only product of random variable. Going from hidden layer to hidden layer, this is W times A, where both are random variable. We've seen how to handle this. Going from the last hidden layer to the output layer, same thing, W times A, we've seen how to handle this. So in all cases, it's always the same form, as Z equals WA plus B. And we've seen using GMA, we can handle that product term here. Same thing for going from a Z hidden unit to an activation unit A through a linearized activation function. Okay, it's going to be a locally linearized activation function. What it means that we specifically, for a given X, we linearize as the expected value of Z, which in turn is going to maintain the overall global nonlinearity of the network between X and Y. Okay, it's going to be locally linear for one specific X, but however, for a different value of X, it's going to maintain the nonlinearity of our activation function. It's important to keep in mind here. And here what's interesting is all of these calculations can be done with closed form linear algebra, meaning it's really simple, it's really efficient. So at the end, in our approximate Gaussian FNN, what we have is going from our prior knowledge for what is our knowledge of the input vector here, X, defined by its mean vector covariance. And given our prior knowledge for the parameter value, meaning the mean vector for theta, its covariance, the output of this approximate Gaussian feedforward neural network is going to be our mean vector for z output, or covariance for z output, as well as the covariance between my output layer, as well as all the parameter theta I have in my network. Okay, so this is important. This is what's going to allow us to learn, okay? The covariance between my output and all the parameters on my previous layer. The last thing I need to know to formulate is how do I go from my output layer to my observations, okay? So there are two setups. In the first setup, we're going to deal with regression. So if we deal with regression, it's fairly simple. We say that our observation layer y is going to be equal to z output, my output layer, or the vector of random variable in my output layer, plus v, which represent observation errors, where v is going to be typically zero mean, normal, or Gaussian random vector with covariance sigma v. So in that case, given that simple observation model, we can calculate mu y being simply mu z and sigma y being sigma z plus sigma v, okay? Now, if we go to a little more complex classification setup, okay, we have to add one more node, because in a classification setup, let's imagine we want to discriminate between bananas and apples. Okay, so if we want to discriminate between bananas and apples, this is what's going to be my label in my class here. And I need to encode this class on my output layer or my observation layer here. So if I have k classes, so apple, bananas, oranges, so I have k equal 3 classes here, I need to encode this into a vector y, which is going to contain real value up to a class. And this is going to be encoded through a conditional probability of banana given real value in my vector y. And this is typically done using the softmax function, okay? But here, why don't we want to use softmax? Is because if we use softmax, we won't have a closed form solution in order to marginalize the uncertainty we have on our output layer into the class. So when I say marginalization, what we have is to express the product of that conditional probability of a class given my observation layer times the posterior probability for the random variable in that output layer given data. So if I multiply both, I'm going to obtain my joint. If I integrate over y, I'm going to obtain my marginal, the marginal probability of a class given data. So if I use softmax, I don't have an analytically tractable solution for this. So instead, what we propose to do is to use a hierarchical binary decomposition, similar to what was proposed by Morin and Bengio. So in that case, if I illustrate how it works for 2 classes, let's imagine we have bananas and apples. So in that case, my index I can take value of 0 for bananas or 1 for apple. So in that case, what I'm going to do, I'm going to represent this as a possible branch, okay? So y is going to be the variable on my observation layer that's going to say, should I branch left or should I branch right? Should I branch toward bananas or apple? So in that case, how am I going to decide as a function of the value y, should I branch left or right? Depends if y is a high or a low value. So if for 0, which are bananas, so I have a high value of y, I'm going to take -1 to the power 0 for bananas. Okay, -1 to the power 0 is going to be 1 times y, if y has a high value. If I look at my CDF function here, which is denoted by that capital phi, so I value is going to give me a high probability. So it's going to be a high probability for bananas if y is high. On the opposite, if y is high and I'm looking for a probability of apple, so apple is encoded by 1, so -1 to the power 1 minus 1 is going to be minus something high. So for a high value of y is going to be a low probability for apples, okay? So here, the power of this method is that we don't have to have only 2 classes. We can stack on top of each other these branches, okay? In this example, I have 3 layers capable of representing 8 classes. And by taking the product over some path in that tree, I can calculate the probability of any of those classes. For instance, in that class on the leaf here. So if I look at the probability of branching right times the probability of branching right times the probability of branching left, this is going to be the probability of that class. So by simply taking the product of 3 terms, I can express the probability of any classes, in this case, up to 8. In the general cases where we have k classes, the number of layers we need to consider is the upper value of the rounding operation for the log in base 2 of my number of classes, okay? So for 8 classes, I need 3 levels. For 1,000,000 classes, I need only 20 levels. So this becomes really, really efficient as the number of classes increases. And as I told you earlier, why do we opt for this? Is because we're going to have a closed form solution to marginalize the output uncertainty, which is going to be jointly normal here. In that case, that result or the outcome of that normal marginalization is going to be given by this term, where I have the product over my H my H level in my tree times the CDF function for each of my level of -1 to my indexes that are given by my index. And here the function inside are going to be mu, where mu is going to be my mean vector for my output layer. Sigma y is going to be my variance for my output layer. And I have a parameter alpha here, which simply scale my CDF function. So one thing we have to keep in mind, there's a little caveat. In order to have that closed form solution for the marginalization, this here assumes that all my variable on my output layer for sigma y are going to be independent on each other, so that the structure of sigma y is diagonal. We're going to explore more later on the implication of that assumption here. So now let's look at how can we solve every step in our approximate Gaussian FNN using linear algebra, okay? So we start from our prior for our weight. So in our weight vector theta, it actually contains all the random variable associated with my weights layer L, my bias layer L, okay? And I have this for all my layers. And this is going to be described, my prior knowledge, by a multivariate Gaussian with mean vector mu theta, covariance sigma theta. Then my joint prior for a jth layer is going to be a concatenation of the random variable for thetas and for A, my activation unit at layer J. And this is going to be a multivariate Gaussian. I'm going to concatenate my mean vector, concatenate all my covariance for sigma theta, sigma A, and my cross covariance, so my dependency between theta and A. So, okay, so then if we explicitly represent the operation for going from an activation unit at layer J to a hidden unit at layer J plus 1 is going to be here all my weights that can be represented in a matrix, a A by A matrix containing all the weights, times my activation units at layer J plus B, my random vector for all my bias. But here again, we have the issue of we have the product of Gaussian random variables. So theoretically, we cannot do that exactly. We need to resort to our GMA, Gaussian multiplicative approximation. And to do this, we're going to reshape these operation as instead of being matrix-wise operation, so a matrix times a vector, I'm going to reorganize all the possible product term into one single vector that's going to contain, since I have A times A terms in my weight matrix, is going to be A squared times 1. Which is going to contain all the possible product operation in these matrix times vector. And using the Gaussian multiplicative approximation, I'm going to be able to calculate the expected vector for this product term, the covariance, as well as the cross covariance between the product terms and all my thetas, all the weight and bias I can have in my neural net. So then what we're going to do, we're simply going to rewrite this equation instead of being the product of a matrix times a vector of random variable, it's going to be a deterministic matrix FWA times a vector FWA, which is a product term, plus FB times B. So let's look at an example to see how does it look like. So here I have the same equation. Now let's look at a trivial example where I have on the layer 1, I have 2 activation units. On the layer 2, I have 2 hidden units, okay? So I want to go from A to Z, okay? So in this case, my Z2 is going to be 2 random variables. My product terms here, I'm going to have 4 of them. So A times W1, A2 times W2, A1's here, A2 times this one. Okay, so I have 4 product terms. This is my vector of W times A term. And finally, my bias, I'm going to have B1, I'm going to have B2 here. So what's the structure for FWA and FB? FWA is going to be simply like this. So in this case, Z1 is going to be A11 times W1 plus A2 times W12. So these correspond to my first 2 terms. So that's why I have 1, 1 and 0, 0. So this term is given by my first line here. The second term is given by my second column, where I have my terms that are here that are defined by my network, okay? So keep in mind that the formulation for FWA is non-unique. It depends on your ordering of your variable in your product term here. And FB in this case is simply a diagonal matrix. So why do we see this? Because I want to show you that we can calculate exactly and analytically all our quantity for the expected value for Z, given by this quantity, for sigma Z, the covariance given by this quantity, and sigma Z theta, the covariance between my hidden units Z at layer J plus 1, and all my parameter theta given by this quantity. So here, I don't want you to pay attention to the specific formulation. I want you to keep in mind that everything we have in black here was already given from our prior knowledge. Everything we have in red and in orange are deterministic matrix that we have. And what is in blue is what can be calculated analytically using our GMA or Gaussian multiplicative approximation. So we have everything in hand to make all those calculations using linear algebra. Okay, so now how do we propagate our uncertainty from our hidden unit Z to our activation unit A? Okay, we have to go through that locally linearized activation function. So we see that A equals sigma tilde of Z. Tilde denotes for the linearization operation. We're going to represent this by a diagonal Jacobian matrix times my random hidden units Z minus its expected value plus sigma Z. Sigma of mu Z. So in that case, J, my Jacobian is diagonal, is basically the gradient vector of representing the partial derivative of my nonlinear function. In this case, I use a soft plus, but could have been any common activation function, evaluated for the mean vector mu Z. Okay, so I linearized all the different locations depending on what's the values in my vector mu Z. So in that case, I can again use linear algebra to calculate the expected value for A, the covariance for A, and the cross covariance between A and theta. So in this case, it's going to be simply Jacobian times my covariance that I've calculated in the previous slide. Okay, so now how can we perform inference? What we've seen so far is how can we go from our prior knowledge for the X, the input vector, and the parameters, and how can we propagate forward that uncertainty? So now we're going to see how can we perform the inference about the weight and bias parameter in our network. So let's consider a data set of our set of observation D, which can be parted into covariance and system response, where these are associated in tuples. So for an ith input vector, I'm going to also have an ith system response. And I have several of those tuples. So what I want to do first is to look at what would be the most intuitive and the simplest way to perform inference. So in that case, we would do the operation we've seen so far of going from our prior knowledge and pushing that knowledge forward to obtain first what's going to be my joint knowledge for the hidden units Z1 and theta, all the parameters in my network. And then I push that knowledge forward to obtain my joint normal PDF for all my parameter theta and ZL. Then for my output layer, then finally the joint knowledge for theta, all of the parameters in my network, so weight and bias, and Y, my output layer. So at the end, this joint PDF is represented by this mean vector and covariance matrix that we've seen in the previous slide. How can we calculate? So now the next step would be to perform the inference. Okay, this is the next logical step of saying, knowing that I've observed Y, how can I infer all the weights and bias in all the layers? So to obtain that conditional distribution, this is my Gaussian conditional we have seen at the beginning of the talk. So in that case, we have closed form solution to perform this, where Y is my actual observation vector that I have obtained in my data set. But there's a problem. This is intractable, meaning that the amount of calculation required here are way too high for this to be of practical interest. Why? Because the size of my matrices are way too big, so it makes it really practically intractable, okay? So if I start from my prior knowledge, so that, for instance, for theta, this represents my covariance matrix for all my weight and bias. So initially, if I assume that this is a full matrix, so represented by a full matrix here, and if I assume that my covariance for my X is diagonal, and I push this knowledge forward, you see that at the first hidden layer, my covariance between my hidden layer Z and theta is going to be almost empty, okay? Then as I'm going to go through layer and layer, this is going to become that covariance between the hidden units and theta more and more full until I end up on the last layer here for the covariance between Y and theta to something that is completely full, okay? And this is problematic because the number of calculation to fill that matrix is really enormous. And also when I am going to use that covariance as well as the joint covariance here for Y in order to apply these Gaussian conditional equation to infer the full matrix for theta, this is computationally intractable, okay? The amount of calculation to do this, it's feasible to do this, but it's not scalable to large problem. Okay, what if we try to simplify the notation by saying instead of using a full covariance, I'm going to use a diagonal covariance. It really speeds up the calculation, but it still remains intractable. Why? Because as we move forward here, these covariance matrix between my hidden units Z and theta still remain full matrices. Okay, so this is still leading to an amount of calculation that is unreasonable. If we want to have tractable inference, what we need to do is to take advantage of the inherent conditional independence we have that is already encoded in a neural network. What does it mean? It means that the layer J plus 1 is statistically independent from a layer J minus 1, given that we know the hidden unit on layer J. Okay, what does it mean? It means that because there are no connection between there are no direct connection between my layer or my hidden vector Z1 and Z3, it means that knowing Z2, Z1 and Z3 are statistically independent. And what does it allow us? It's going to allow us to work with pairwise consideration of layer. Okay, and that greatly improved the computational efficiency. So let me detail this. So we still start from our prior knowledge for X and theta. And then what I do, I'm going to propagate forward that uncertainty, but only by storing the information for that specific pair of layer. So meaning my joint knowledge for my input vector X and my my hidden units Z for layer 1. So same thing for my covariance or my joint knowledge for the parameter theta 0. So only the parameters, so weight and bias, involved in that layer. And my joint knowledge for Z1, my first hidden layer. And I do this, I go forward. So here I'm going to have only the knowledge for my last hidden layer and my output layer, the theta parameter theta L for that specific layer, and my hidden layer here for the output. Sorry, my output layer is Z0. And finally, I'm going to have my joint for Z0 and Y. And then when it's time to do inference, we're going to do the inference, instead of doing the inference for all the parameters at once, we're going to take advantage of that inherent conditional independence to make pairwise inference. Okay? So using the same Gaussian conditional equation, knowing of having observed Y, I'm going to infer what is Z on my output layer. Okay? Using the same Gaussian conditional equation as before. Now for going from my posterior knowledge for my hidden units on the output layer, I'm going to do the inference for simply the parameter on this last layer, okay? And to do this, we have to modify slightly the equation, because now instead of using the plain Gaussian conditional equation, we have to use the recurrent RTS estimation, okay? So in that case, we are going to review the notation. So the parameter at layer J is going to be simply theta. The hidden unit at layer J is going to be simply Z. The parameter at layer J plus 1 is going to be theta plus. The hidden unit at layer J plus 1 is going to be Z plus. Okay, so Z plus is the layer J plus 1. Z is going to be layer J. Okay, and we can just rewrite our equation here for the recurrent RTS estimation to say that given my knowledge for my random vector ZO, my posterior knowledge, I infer my posterior knowledge for theta for the output layer. Then I do the same thing, but to infer the value for the last hidden layer from my posterior knowledge for the output layer. And I keep going back like this, hopping from pair of layers to pair of layers. And this is highly efficient, contrary to what we've seen before. Sorry. Why? Because we only need to store matrices that are much smaller. For instance, if I start with a full covariance matrix for theta and diagonal covariance matrix for x, so in that case, I only need to store a covariance between x and z1, okay? And the covariance between theta and z is only theta 0 and z, okay? Which is much smaller. So right now, all of these are full, but of much smaller size. And at the end, my covariance here for z and y, so z0 and y. And then I do the backward operation. And in this case, this is still intractable. Okay, this is still require way too much calculation. But what we can see is that if we add to this the hypothesis of having a diagonal structure for both my parameter theta as well as my hidden unit z, then the size of matrices shrink drastically. Okay, so now my covariance between theta and z becomes heavily sparse. And this is true for all my layers. The only matrices that remain non-sparse are going to be the covariance between x and z, z and z plus. And here the interesting property is that at most, I'm going to have less or equal to a squared plus a non-zero terms in any of the matrices I need to store. Okay, so what does it correspond? A squared to a. Remember, for two successive hidden units, hidden layers, we assume that in each of those hidden layers, we have a hidden units. Okay, so there are a square possible connection between them. So what it means is that the overall storage and computational complexity of doing these forward propagation uncertainty or inference is going to be OA squared, or basically is going to be a linear computational complexity with respect to n, where n is the number of weights in my network. And this brings it at par with backpropagation. So the computational complexity of this TAGI is the same as using backpropagation, except that here we have no gradient whatsoever, okay? Everything is learned in a Bayesian way, where we consider the uncertainty from the input layer to the output layer, okay? But here, there's one thing that remains to be answered. Okay, but this hypothesis of using diagonal structure for theta and z, to what extent is it valid? Okay, to what extent is it going to affect the result? We're going to look at this through the benchmark later on. Okay, so before looking at the benchmark, there's one last thing we'll need to look at together. How do we estimate I per parameter? Okay, because one of the issues that in neural net, we might have millions of weight and bias parameters. Okay, and it's going to be impossible to define a proper prior knowledge for the mean vector and the covariance matrix. Okay, typically what we're going to do, we're going to initialize that mean vector for, which is our I per parameter for our knowledge of theta. We're going to initialize this randomly, and we're going to initialize our covariance at a fixed constant. Okay, so here our parameter theta are our parameter, but the joint PDF for these parameters are parameterized by the mean vector and covariance, which are represented by eta here, my I per parameters. And since I'm going to have initially really poor choice for these I per parameter, the predictive performance and the learning performance is going to be poor as well. So one way to go around this would be to use full Bayes, okay? Not only infer the parameters, but the hyperparameters as well, okay? So in that case, it's going to be the likelihood of my data given my parameters times my prior knowledge for the parameters given my hyperparameters times the prior for my hyperparameters. So this is the full Bayes approach. But the problem is this is intractable, okay? Even using GMA, we cannot solve this. So one solution to do this is to use empirical Bayes, okay? Instead of using the full joint estimation for theta and eta, we're going to use a point estimate for eta. The point estimate is the value of hyperparameter that maximize the marginalization of, so the integral over theta of my likelihood times my prior given eta, okay? So the problem here is that this is also intractable. Why? Because in the first place, the whole reason of doing that TAGI, that approximate analytical inference, is to say we don't want to optimize. We don't want to use gradient. We don't want to solve that maximization problem. We want to do exact inference. So if we have to now do a maximization problem to infer these quantity, we'll just go around the point, okay? And especially that there are way many more hyperparameter than they are parameter themselves. So this just kills the solution. We cannot go with a traditional empirical Bayes. But there's a nice solution to go around this. What we can do is simply to use TAGI recursively over multiple epochs, meaning we're going to see several times the same data, okay? Typically, we cannot do this with Bayes, okay? Because we go at the risk of overfitting, okay? So what we're going to do here to prevent overfitting is that we're going to stop this procedure of using recursively the same data by looking at our performance on the validation log likelihood on a validation set. So how it works, I go from my prior knowledge for these hyperparameters. So my prior knowledge, my randomly initialized mean vector and covariance, and I'm going to obtain using TAGI a first estimate or a new estimate for my mean vector and covariance. Then I'm going to use that newly inferred knowledge as my prior, and I'm going to obtain another estimate. And I'm going to loop on this until I obtain an optimal number of epoch that was found using a validation set. Okay, let's look at this in more detail. We're going to look at this through a toy problem. What we have here is a deterministic function that relates output y to covariate x. And we're going to model this using a simple toy neural network, which has one covariate, one system response. I'm going to have one hidden layer with 100 hidden units. Okay. So in this case, the black dots represent my actual observation for training my neural network. So if I plot the prediction of my Bayesian neural network, the red line is going to be the predicted expected value, and the pink region is going to be the plus and minus 3 standard deviation. This is for epoch 0. This is before using any data, okay? What about when I finish my first epoch? So I've seen only once each of those 20 data points. So we see that the approximation or the learning is pretty poor. What if, instead of using only one epoch, I look at what's going to be my log likelihood over several epoch, okay? So here you see, this is the result I have obtained after 50 epoch. You see that if we evaluate the log likelihood of my neural network on the training set, it's going to keep increasing, okay? However, if I use these pink diamonds, which are actually a validation set that was never used to train the model, only to test here the performance for my validation set. So in that case, I realize that if I go beyond 24 epoch, actually the performance at predicting unobserved data starts to decrease. So in that case, we can see that the optimal number of epoch, if we want to prevent overfitting, would be 24. Okay, the difference between 50 and 24 is slight, but we can see on the validation set that the performance decreases. So now we're going to look at we're going to investigate the effect of assuming that instead of having a full covariance structure for hidden units z and for our parameter theta, we use a diagonal, okay? How bad or how good is that approximation of a diagonal? And we're gonna investigate this by saying, okay, we no more make the hypothesis of a diagonal structure. We're gonna look at the full covariance matrices, okay? So it makes the calculation way slower, but let's look at what would be the resulting covariance if we infer using full structures. So for the same problem, this is what we would obtain. So this would be, for the full covariance structure, the prediction from the model at the 0th epoch, so before seeing any data. This would be the output of the model after 50 epochs. So we see the really similar behavior to what we had before. But now what is interesting is what we have on these graphs here. So the top left graph is going to be all the possible correlation coefficients in my covariance matrix between any pair theta I, theta j. So the horizontal axis here is the number of observations for the first epoch. Okay, so this is the first line of pixel is what is going to be my correlation coefficient in the upper diagonal part of my correlation matrix for my covariance for theta I and theta j. So here the color is green is 0, +1 is dark red, and -1 is dark blue. So what we can see here is the first top half is the parameter for going from X to my first hidden layer. The second half is from going from my hidden layer to my output layer. What we can see here is that everywhere on the first epoch, and then so this is for each observation, my first epoch. Then on the second graph, we go not for observation to observation, but from epoch to epoch. Okay, and we see across the board, we have almost no correlation. So even if we consider the full correlation structure, the end result that the network infer is that the correct answer is no correlation at all. We have here some correlation, some negative correlation for some of the parameters. The graph on the bottom is what is going to be the correlation structure, but this time, instead of being for the parameter theta, it's for the z, the hidden units on my hidden layer, okay? Again, everywhere my correlation is almost 0, except for some values that are slightly different from 0, okay? Here the structure is because I've sorted the value of the correlation coefficient, so the small ones are all on the bottom, the high ones are all on the top. Okay, so here this confirms that even if we use the full covariance, the result of inferring with the full covariance is that the output, the posterior, is quasi-diagonal. Okay, what if we change the structure and instead of considering a single hidden layer, we have 2 hidden layers? So in that case, we have exactly the same results for the parameters. So the covariance for the parameter is still diagonal, but we have something slightly different because here the Z1 is going to be the covariance for my first hidden layer. The Z2 is going to be the covariance for the second hidden layer. So for the second hidden layer, we see that there are some dependency appearing, but this. And here, remember, the first bottom graph on the left is going to be for each observation from the first epoch. So we see that we have significant positive correlation during the first epoch. But during the first epoch, there's almost nothing that's been learned yet. But what we see if we go on the graph on the right, the last line here for the graph on the left represents the first line on the right here, okay? But then as we go from epoch to epoch and we start to learn the behavior, we see that the correlation between our hidden units simply vanishes, okay? So that shows that even if we use the full covariance structure, the end result corresponds to our assumption in the first place, that both the covariance for theta is diagonal and covariance for z is diagonal as well. So by doing the shortcut in the first place, we can save a great amount of calculation and end up at the same place at the end, okay? So this really illustrates the power of the hypothesis we're taking here. So let's now look how the method compare in terms of performance to other existing methods. So here we're going to compare for some regression benchmark with PBP, VMG, and MC dropout, okay? So here you see that we have several regression benchmark dataset for which we evaluate the performance. On the left, you see the root mean square error, where the lesser is better. And on the right, you see the average log likelihood, where the higher is, the better. So the method that scored the best is going to be in orange. The method that scored the second best is going to be in teal or green color. Okay, so what we can see by looking at this is that obviously VMG seems to outperform all the other methods. But here we have to keep in mind the efficiency of the method, because both TAGI, PBP, and MC dropout are roughly have all the same computational time. They're all pretty efficient. However, VMG, that seems to outperform in terms of predictive performance, is more than 100 times slower than these other three methods. So of course, okay, it works better, but it is at the cost of a much higher computational time. Also, if we look at which would be if we exclude VMG, we see that sometimes MC dropout is better, sometimes it's TAGI. Same for the log likelihood. Sometimes MC dropout is better, sometimes it's TAGI. But take into account that MC dropout will take into account the heteroscedasticity in the observation error, which TAGI doesn't yet consider. Okay, so there are several things, and it also uses dropout. So there are several featured MC dropouts used that TAGI doesn't use yet. So this is a much more basic network or configuration that this is, and it performs roughly at par with this. And in all cases, MC dropout and TAGI, they both outperform PBP. Another thing we have to be careful in that comparison, it's done with a fixed number of epoch equal to 40. Okay, if we want to have a fair comparison, we would need to compare with by optimizing the number of epoch for each approach. Now let's look at a second benchmark. We're going to look at the MNIST classification, where we have images of size 28 by 28 of 10 classes from 0 to 9, where we have 60,000 of these images to train and 10,000 to test. So our network configuration here, since we have 28 by 28 pixels in the input, I'm going to have 784 nodes on my input layer. Then I'm going to have 2 hidden layers, each comprising different number of hidden units. And on my output layer, I'm going to have 11 nodes that are going to be compatible with my hierarchical binary decomposition. And even if I have 11 nodes, every time I update, I only need to update for 4 of those layers because I have 4 levels in my tree. Okay, so in that case, if we look at the performance of TAGI, for A equals 100 or A equals 800 hidden units, okay? If we look at the performance in terms of classification error, the percentage of the time where the predicted label is wrong is going to be 3.5% for 100 hidden units, 3.2% for 800. And this is for using a single epoch. If we run over multiple epochs, so in this case, the optimal number of epoch is 12, in this second case is 8, the performance dropped to, or increased to 2.4% versus 1.5% for 800 hidden units. How does it compare with a normal neural network? So the state-of-the-art performance for that same architecture for 2 hidden layer, 800 hidden units is 1.6% for standard feed-forward neural network. So we said we match the performance of the state-of-the-art. So this is also obtained using a single observation per batch. And keep in mind that this is not possible with a standard neural network. In our case, we can either use 1 observation per batch or multiple observation per batch. We're going to reach roughly the same performance. Okay, so now let's look at the performance we have here, the capacity to learn quite well using a single epoch. Okay, we're going to dig a little deeper in that hypothesis. How good are we at learning with a single epoch? So first, we're going to look at what is going to be our predictive performance in a probabilistic manner. Okay, so this is representing my prior knowledge. So what is going to be the probability predicted for each class for my 0 observation, just my prior knowledge. So this graph we see on the left is the probability for each of the possible label for all the observation in my test set. So I have 10,000 observations, okay? So each pixel in this graph represents the probability going from 0 dark blue to 1 dark red for each of the classes. So right now I haven't seen observation, I just have my prior knowledge, and basically all of this is a probability that is roughly around 10%. So basically say I have equal probability for each of my classes. Okay, so these are the real true labels that have been sorted. This is the predicted label. Okay, what I have on the right is going to be my probability of correct or incorrect classification. So what I have in white is my probability of correct classification, okay? Meaning that for the correct test set label, the probability of the class I'm predicting is the highest among all classes, and it's above a threshold 5. Okay, so in that case, we see that since we have no observation, this goes around 10%. Okay, 10% of the time, since we're predicting at random, we're right. The black one is the opposite. Okay, so the highest class, the highest probability among all classes is the wrong classes. Okay, and in order to say that it's an incorrect class, that probability needs to be above a threshold 5. So if I'm not above a threshold 5, I'm going to say I don't know. Okay, I won't do a prognostic. I won't say which class is it. I'm just going to return I don't know. Okay, so in that case, we can see that with no knowledge, we can really tackle correctly the uncertainty. What if we use for a single epoch, 60 observation, okay? So 6 observation per class. We see that we can start to learn, okay? Whenever we see color that are going through the red on the main diagonal means that the predicted label and the test label are in accordance with high probability. And we can see that here, the white region increases, and this is using one epoch, 60 observations. What if instead of a 60 observation, I use 600? You see that it increases even more, and we see that everything aligned with high probability on the diagonal, 6,000, 60,000, okay? All these results were with one epoch, okay? Okay, how good is this compared to what's currently existing? So this is on top with TAGI using the online analytical inference. What you see on the bottom would be what would be the classification result for the same display, but this time using a standard neural network that's going to rely on gradient backpropagation. So in that case, in order to achieve this result, we need over 100 epoch, okay? What would I have obtained as a graph if instead of using 100 epoch with a standard neural net with backprop, I use a single epoch? You see that the performance here is really catastrophic. Actually, it performed worse than just using no observation with TAGI. Okay, so here we see that we completely overfit some classes and the result is really poor, because here when you rely on backprop, it's not meant, it's not supposed to work by looking at a single epoch. You need to see your data over and over again. This is what prevents you to do online inference, to do online learning, whereas with TAGI, this is built in the network. So in conclusion, what I have presented here is what we develop, what we call Tractable Approximate Gaussian Inference, TAGI. So what it allowed to do, it allowed to do the analytical inference for the posterior mean vector and diagonal covariance matrix. It will allow to do end-to-end treatment of uncertainty from the input layer to the output layer. And this is going to allow some really new architecture or some really new development in machine learning. For instance, if you can have end-to-end treatment of uncertainty from output layer to output, it will allow you to do online RNN. It will allow you to do partially observable reinforcement learning, okay? Then it allows to do Bayesian estimation using a single observation at the time. This was not possible before. And really interestingly, it has a linear complexity with respect to the number of weight, meaning we can really scale it to large number of parameters. Okay, then if it's that scalable, why haven't we tested with more complex benchmarks such as ImageNet? The thing is that here we have to build and we have to code everything on our own, okay? We cannot rely on anything such as TensorFlow or PyTorch or any of the existing libraries, okay? They are useless for our case here because the inference engine is completely different, okay? So all of the architecture, we need to recode them ourselves, so that takes time. That's why we don't have yet big benchmarks such as ImageNet of those, but these with time will come. And finally, what I can say is that for the architecture we could test using feedforward neural network, for the same architecture, it matches the performance of existing method using backpropagation. And this can be done using, in our case, only one observation or multiple observation at a time. So if you want to have more detail about how can you use the code to reproduce these results, look at the subsequent video on the same channel, which will present the detail of how can you use our code that we're going to publish online to reproduce these results.